Welcome to the fascinating world of mollusks. Imagine you are a soft, squishy creature living in a harsh, dangerous world filled with sharp rocks, crushing waves, and hungry predators. How would you survive without a skeleton inside your body to protect your vital organs? You would probably build a tough, portable house to carry on your back, much like a snail does. Or you might develop incredible intelligence and camouflage like an octopus. This is exactly what the animals in the phylum Mollusca have done over millions of years of evolution. By understanding them, we get to see one of nature's most successful and diverse survival strategies in action. Now that we have introduced these incredible creatures, let us formally define what makes an animal a mollusk. In formal biological terms, Mollusca is a major phylum of invertebrate animals, characterized by a soft, unsegmented body. The name itself comes from the Latin word mollus, which literally translates to soft. Because they lack an internal skeleton, they have had to evolve wildly different ways to survive in harsh environments. Some, like the slow-moving garden snail, secrete a tough calcareous shell for protection. Others, like the jet-propelled squid, have abandoned the heavy shell entirely, relying instead on speed, camouflage, and remarkable intelligence to evade predators. Building on that basic definition, let us look at the specific anatomical features that almost all mollusks share. Every typical mollusk has three fundamental body regions. First is a muscular foot, which is primarily used for movement. Second is the visceral mass, which safely houses all the internal organs. Third is the mantle, a heavy fold of tissue draping over the visceral mass that actually secretes the hard calcareous shell. Additionally, most mollusks possess a unique feeding organ called a radula, which acts like a ribbon of tiny chitinous teeth used to scrape food off surfaces. Finally, they are true coelomates, meaning they possess a fluid-filled body cavity completely lined by mesoderm tissue, though it is often reduced in adults. To better visualize these core characteristics we just discussed, let us examine this diagram of a hypothetical ancestral mollusk. This represents the foundational blueprint from which all modern mollusks evolved. At the very bottom, you can see the large, flat, muscular foot, which anchors the animal and allows it to crawl. Resting directly above the foot is the visceral mass, where the digestive and reproductive organs are packed together. Notice the thin layer of tissue covering this mass? That is the mantle. The mantle's primary job is to secrete the thick, protective, calcareous shell you see forming the outermost dome. Finally, look at the mouth region on the left. You can clearly see the radula, the specialized toothed ribbon they use to scrape up food. Having seen their anatomy, you might wonder why we spend so much time studying these soft-bodied creatures in university zoology. The truth is, mollusks are incredibly important to both global ecosystems and human economies. Ecologically, bivalves like oysters act as nature's water filters, cleaning thousands of gallons of ocean water daily and maintaining the health of marine habitats. Economically, they provide a massive global food source and are the sole creators of natural pearls, driving trade for centuries. Furthermore, studying the complex nervous system of cephalopods, like the octopus, helps neuroscientists understand the evolution of intelligence and memory. If mollusks were to disappear, marine food webs would collapse, and we would lose vital bioindicators that warn us about ocean pollution. While biology often feels purely descriptive, the growth of a mollusk shell provides a beautiful example of mathematics in nature, which brings us to our first formula. As a snail grows, its mantle secretes new shell material at the opening, creating a shape known as a logarithmic spiral. This allows the animal to grow larger without changing its basic proportions. The formula is R equals A times E raised to the power of K times theta. Here, R is the radius of the shell from its center. The symbol A is the initial starting radius when the mollusk is just a baby. The constant E is the base of the natural logarithm. The variable K is the growth rate constant. If K increases, the shell expands outward much faster, creating a loose spiral like a clam. But if K is small, it coils tightly like a garden snail. Finally, theta represents the angle of rotation in radians. Before we move on, let us see this formula in action with a concrete example. A marine biologist is studying a sea snail whose initial baby shell radius, A, is 2 millimeters. The growth constant, K, is 0.1. We need to find the shell radius, R, after one full rotation, which means theta is 2 pi radians. First, we convert the full rotation into a standard decimal, giving us 6.283 radians. Next, we multiply the growth constant by this angle to find our exponent, yielding 0.6283. We then raise the mathematical constant e to this power, which gives us an intermediate growth factor of approximately 1.874. Finally, we multiply this factor by our initial radius of 2. The final answer is 3.748 millimeters. Physically, this means that after one full 360-degree turn of growth, the opening of the snail's shell is exactly 3.748 millimeters away from the center. Now that we have modeled their shells, let us look at how we mathematically classify their feeding structures. Taxonomists use a mathematical radular formula to classify gastropods based on the arrangement of teeth on their radula. The formula is R equals 2 times M plus 2 times L plus C. In this equation, R represents the total number of teeth in a single horizontal row. M is the number of marginal teeth on one side, and L is the number of lateral teeth on one side. We multiply these by 2 because the teeth exist symmetrically on both sides of the mouth. Finally, C represents the single central or rachidian tooth. If a species evolves more complex feeding habits, the values of M and L will generally increase, changing the total tooth count. Let us apply this radular formula to identify a specific specimen. We are given a snail where the central tooth count, C, is 1. The lateral teeth count on each side, L, is 3, and the marginal teeth count on each side, M, is 12. We need to calculate the total number of teeth in one transverse row. We substitute these values into our equation, placing the numbers in parentheses to clearly indicate multiplication. This setup perfectly mirrors the biological symmetry of the animal's mouth. We perform the basic multiplication first, yielding 24 marginal teeth and 6 lateral teeth in total. Then we add these to the single central tooth. The final answer is 31. This means there are exactly 31 teeth in a single horizontal row. Because different families have highly specific formulas, this exact number allows biologists to accurately classify the specimen. Having calculated the specific traits used for identification, we must now look at how scientists organize this massive group of animals. According to the authoritative classification by R.D. Barnes, the phylum Mollusca is divided into several distinct classes based primarily on the type of shell, the shape of the foot, and the nervous system. Let us start with the more unusual deep-sea classes. The first class is Aplacophora, which are strange worm-like mollusks that completely lack a shell. Next is Polyplacophora, commonly known as chitons, which are easily recognized by their tough, eight-plated dorsal armor. Then we have the class Monoplacophora, which contains rare deep-sea creatures with a single cap-like shell. Interestingly, these were once thought to be entirely extinct before living specimens were discovered. Moving from the deep sea to more familiar environments, we encounter the most common classes of mollusks. First is Gastropoda, which is the largest and most diverse class, including all snails and slugs. Gastropods are famous for undergoing a unique developmental process called torsion, which literally twists their internal organs into a figure-8 shape inside their shells. Next is the class Bivalvia, which includes clams, oysters, and mussels. Unlike gastropods, bivalves have completely lost their radula. Instead, their bodies are enclosed in two hinged shells, and they have adapted perfectly to a stationary, filter-feeding lifestyle, pulling nutrients directly from the water column. Finally, let us explore the last two major classes in Barnes' classification system. The class Scaphopoda, commonly known as tusk shells, features animals with a unique tubular shell that is open at both ends. These creatures live buried deep in the ocean sand. Then we reach the pinnacle of molluscan evolution, the class Cephalopoda, which includes octopuses, squids, and cuttlefish. These are the most advanced mollusks by far. In cephalopods, the ancestral muscular foot has evolved into complex tentacles and a siphon used for high-speed jet propulsion. Accompanied by a highly developed brain and complex nervous system, cephalopods prove that you do not need an internal skeleton to become an apex predator. To wrap up our journey through the phylum Mollusca, let us review the key takeaways. Remember that these animals are defined by their soft bodies, muscular foot, mantle, and radula. We've seen how their shell growth and tooth arrangements can be perfectly modeled using mathematics. Despite sharing a basic blueprint, they have evolved into a staggering variety of forms, from the heavily armored chitons to the highly intelligent, shellless octopuses. By mastering this classification system, you can now look at any mollusk and understand the evolutionary choices it made to survive. Excellent work today. You have successfully covered the foundational characteristics of this incredible phylum.